How's that?
Looks great.
All right, welcome everyone. Thanks for joining us. You're here on day 2 of our Modeling Expo. We're so excited to have you. We're especially grateful to the amazing lineup of speakers that are going to be telling us about their models today. I'm Marin Clark. I'm a professor at the University of Michigan in the Department of Earth and Environmental Sciences, and I'm the lead PI of the Center for Land Surface Hazards Catalyst, or CLASH. And so I want to tell you just a little bit about our effort before we jump right into those exciting modeling talks. So first is why CLASH? So why do we need a focused study of land surface hazards? And if you advance the slide, yeah, so this is it in one graph here. Land surface hazards are everywhere. They're not just confined to the plate boundaries, and we're seeing them increase with a changing climate and changes in land use and expansion of urban population into parts of the world where people didn't live in such numbers before. And so as such, we're seeing a really rapid acceleration in the threat from land surface hazards. And one that even starts to outpace more well-funded groups like volcanic and earthquake hazards. And we're seeing an increase in the interest and attention paid to land surface hazards. So then what is CLASH? I want to tell you a little bit about our effort. NSF launched a new initiative last year in geohazards, and as part of this program, they funded 4 trial centers or center catalysts. And so these are 2-year grants supported to pilot center activities, such as this Modeling Expo, and to host community events, community building events. So they operate much like the RCNs, the Research Coordination Networks. And the purpose is to bring the scientific community together to ideate and strategize about how community level efforts can advance science research in big ways. Sorry, step back for just one sec, Josh. So this effort is a part of solid earth science, but we have really obvious connections to atmospheric science. We got to hear a lot about that yesterday, some climate and environmental forcing. And also to social science and engineering, which we're going to hear a lot more about today. So we're building out the science vision that relates us in the solid earth hazards to those other groups. Okay, so the exciting initiative that we're going to talk about today is the hazard cascade. And so I want to give you just a little figure of what we see as the hazard cascade. This is not a new idea. This idea has been around for some time, but it's really gaining a lot of traction in the scientific research world in recent years. And we see that this is really the ripe time and that it's a novel opportunity to advance science innovation in the hazards world. And so the way that this works is that with a triggering event, there's a large impact. But because of that initial triggering event, subsequent events that come in after are magnified by the fact that they occur in a short time sequence from the initial triggering event, creating this downstream scaling or cascading effect of hazards. And so some examples in the next slide, ones that you might be familiar with, are ones that, for example, tie earthquakes with landslides and flooding. So earthquakes can trigger many landslides throughout the landscape. These landslide debris can dam rivers. That damming can create flood risk or aggradation and later flooding, sometimes years to decades following the initial trigger, which in this case would be the earthquake. Fires, wildfires are another one that are really on our mind, especially in the western part of the US. Wildfire dramatically alters the land surface conditions, making an acceleration of erosion processes and alterations of carbon flux. And then we can also think about interactions with the cryosphere in the face of a warming planet and how warming temperatures in the Arctic can cause, and at high elevation, can cause ground failure and flooding. And so the last point I want to talk about is just who is Clash. So I'll introduce you to our team. We have 4 PIs, myself, joined by the Joshes, Josh West and Josh Roering, and Demetrius Ekos. We're also joined by a big, energetic, early career team of 7 that make up our steering committee. And we have over a dozen partner organizations that have all agreed to be a part of our pilot projects as we move through this 2-year grant. And then importantly, all of you. So you're at the top of this page, right above the Clash team. And I just want to emphasize that one of the goals of having this modeling expo is to involve the scientific community in shaping the vision of the future Center for Land Surface Hazards Research. So with that, I'm excited to hear from you all and to hear these talks. And I'm going to turn it over to my co-PI, Josh Roering, who's going to tell you a little more about the Modeling Expo vision and what we have in store for you next.
Thanks, Marin. Let me get my slides dialed in here. I'm going to tell you a little bit about a little bit about the Modeling Expo in general, and then talk about our first session to kick it off here. So if you can give me a heads up as to whether I'm getting you slides in presentation mode. Does that look good?
Josh.
Okay, great. Thanks. As Marin pointed out, hazard cascades are kind of a thing. It's not just in the science world. You start to see them in the popular literature, out in the press. And so that means we can characterize it, define it, start to model it, and use it to answer questions. And I think that's what has led us to this Modeling Expo, which is the brainchild of our collaborator, Demetrius Ekos. So an expo is a place to highlight things. It's a showcase, it's an exposition, it's a conference. And so we're really here just to sort of see what's out there in terms of models that address these various processes that are components of the hazard cascade. And yesterday I mentioned that this just, reminds me so much of growing up in the Midwest and going to a boat expo. And that is just burned in my brain. And you'd see everything from canoes to yachts, everything that was water going you could find at the boat expo. And that's kind of the mentality we wanted to have here, is just to say, bring your models, help us understand how these things might be used to understand these hazard cascades. There's no single model that's going to serve all of your water going needs, and same thing for your boat going needs, or sorry, your modeling hazard cascade needs. So I'm mixing my metaphors here. So we're not here to pick favorites or hand out awards or anything. We want to build community by showing, highlighting some of these disciplinary tools that we can use to help improve prediction of hazard cascades. We have been presented with this challenge from society, and we hope Clash can be an intellectual hub for some of these activities. So yesterday we covered some fantastic ground. Today we're going to get into hydrology, landslides, sediment transport, and then finally exposure and risk, something that doesn't happen that much for us in the solid earth world. And so I'm excited for that sort of span of everything from bedrock weathering to insurance. That's what we're covering here. And so with that, I want to thank our team and thank all of you for being engaged today so far. And here's the way it's going to work. We're going to go from session to session. It's being recorded. Jump in, jump out as you can. So as your schedule allows, we welcome you anytime. Input is going to be at the end of each session's last speaker. So we're saving a chunk of time. In the meantime, though, please use the Zoom chat. So throw your questions in the Zoom chat. Also, there's a Google Doc that Jill will be posting that you can use to post questions and input there. So please do those in real time as they're coming to you. Don't wait. Just throw those in there. If you have any questions, specific, general, we want to get to any level of input and feedback that you have. There's a timer that Jill will have on her screen that you can see if you're a speaker to keep us on track. And if anything comes up, Adriana can be reached on that email address right here. Just give her a shout if you're having Zoom issues or getting in and out of the waiting room or otherwise. There is a code of conduct, so if there's anything out there nefarious, we would love to know about it. Please keep this open and respectful environment and community. And with that, I think what I'd like to do is just briefly introduce our first session, hydrology and flood routing. Pictures like this are the stuff of news reports and 101 lectures that a lot of us have been in and perhaps given. And to be honest, it was one of the first opportunities to introduce probability and quantitative thinking to students. If you've taught a class on flood frequency, you've had students plot discharge and plot recurrence interval and think about the frequency with which floods inundate certain parts of the landscape. And that's this really empowering moment for students. If I think back, the challenge then is you tell them that, well, climate and other things are changing that. And so the statistics are not stationary, and you can watch their sort of brains start to explode and think about the challenge of managing Earth as humans in this changing regime. So this is a big business, a lot of interesting science questions, and I'm super excited by the slate of speakers. Paul Bates from Bristol and also Fathom is going to kick it off with his work, and then I'm going to pass it to my colleague Brian Yanites, Francis, Giuseppe, and then Lauren is going to finish it off, and I'll introduce them real briefly as we go. But Paul, thank you for being here in the UK on your evening. Paul has broad experience modeling global scale floods, and it's an absolute pleasure to have him here. And so I'll stop sharing, and you can take it away from there, Paul. Thanks so much for being here.
Thank you very much, Josh. It's a pleasure, and thank you very much for inviting me. You guys see all this in, well, you don't want to see the conclusions.
Eventually.
Eventually, yeah, we're going to do it backwards. I mean, it's all right, let me just get rid of the screen controls as well. All right, okay, hopefully everybody can see that. Okay, so I'm going to talk a little bit about our research modeling flood risk across the US. And what we want to do in this research is model fluvial, pluvial, and coastal flood hazard, both now and under future climates. And we want to do that at high resolution across a range of return periods. It's quite a big team that's done this work. It's probably between about 50 and 70 person years of effort to get to this point. And you can't actually leverage that out of standard research grants in the UK. So it's both work by my university research group at Bristol, but also through Fathom, a company we co-founded a while back, that we can use to generate commercial money to fund this research going forward. Okay, so how do we do flood modeling, inundation modeling? How do we predict which areas are at risk? Well, at small scales, we know that classical hydrodynamic codes work really well. And this is an animation of a site here in the UK that we've modeled a little bit over time. But the challenge is, how do we move from those small scale models up to models that cover entire countries or even continents and have the same resolution and fidelity? Well, the answer to that, we decided, was to build a software that automatically generates these small scale models, many instances of them across a whole territory. So across the US, we have somewhere between 50 and 100,000 individual 2D models built automatically from publicly available data. So what that gives you is a whole US 2D hydrodynamic model. It's solving the local inertial version of the shallow water equations, all flooding hazards for 6 different return periods. We look at compound events in the coastal zone. 30-meter resolution is native, and we can downscale where we have a very good DTM. We've got a detailed hydrography based on the US data. We use a regional flood frequency analysis for our boundary conditions. We have a channel solver to solve for the unknown bathymetry, because clearly that's not there in any of the digital elevation data. And we include all the local adaptations that we can, and do that for both historic, current, and future conditions. So the work's published in this paper in WRR, and you can have a look in there for a bit more information. And so we even include things like methods to automatically detect flood defenses and get those into the model. And this, of course, makes a huge difference to getting realistic results out. So as Josh was saying, you do have to fuse the social, the human, with the physical in these schemes. So how does it work? Well, we can look at the comparison of our models of both FEMA, special flood hazard maps, and USGS models in particular places. I'm not going to go through this in detail, but basically blue is where the model's doing well, and red and black are the misses and the false alarms. Possibly the best metric is this critical success index in the third column. And generally, when you get a value over about 0.7, your model is doing as well as can be expected, given the typical errors in the data. So in many places, we do as good as local modeling with hydrodynamic models. Not always, but taken as a whole, we do pretty good. And here's some comparisons between some locally built models by the Iowa Flood Center. So this is their 1 in 100-year hazard maps for fluvial flooding across Iowa. And we can, again, look at positives, false negatives, and a critical success index getting towards 0.9, which is exceptionally good. So these models can work really well. I'm not cherry picking here. They genuinely do a very good job in quite a lot of places. So this is what the results look like. This is Dallas 1 in 100-year fluvial hazard. You can see with the red vectors are where we have known flood defenses. Here's the same city, Dallas. This is now pluvial flooding, 1 in 20-year, and you can see how that's picking out some of the creek network that's not there in the main rivers. And this is Houston coastal flooding in 2020, and the extension due to sea level rise and change in storm surge out to 2050 as well. So we can start to play these really useful, experiments and tests. What do we find with all this? Well, panel A here shows the 100-year flood inundation in 2020 in kilometers squared, and we've discretized that to 1 degree tile. So you can see the concentrations of 1 degree tiles where there's a concentration of area land at risk of flooding. Panel B is the change in inundated area between 2020 and 2050. And you can see that in the particular climate scenario we used here, there's quite an extensive drying signal across much of central and southwestern US, and very strong increases along each seaboard. And also we're able to do things like, well, let's have a look at the area behind flood defenses that we're going to lose that standard of protection for, even over a 30-year period. And in other papers, we've looked at how this changes exposure and risk, social justice, and also we looked at mitigation strategies. And very importantly, when we do this analysis with our models, we show large differences between the exposure, the number of properties and people at risk from flooding, compared to the results you get if you take FEMA special flood hazard maps. So this is number of times more property at risk down to county level across the US compared to FEMA data in our model. So you can see some very important differences there. And as you can imagine, that's gained an awful lot of press attention. But so that's just a whirlwind tour through the kind of modeling that we can now do. And that's it. Thank you very much.
That was spectacular, Paul. Very efficient and time to spare. We really appreciate that worldview. We're gonna, as much as I'd love to jump into some questions, we're gonna just save those. There's a couple coming into the Google chat, or sorry, Google Doc, and others, please just chuck them in the Zoom chat, whatever you're most comfortable with. There's links in the chat. And let's, with that, move to the next speaker. Thanks so much, Paul. That was spectacular.
Thanks very much.
Brian Yanites, take it away.
All right. You see that all right? All right, great. Thanks, Josh. So I'm going to give you a case study of flood routing from some work a PhD student, Clark Delisle, has done. So like I said, this is not primarily my work. This is PhD student Clark, who actually just defended on Thursday. And this was a side project of his. And so I decided to take the lift off his shoulders and do the presentation today. But we're going to look at the cascading flood hazard following a rather extreme rainfall event in southern Taiwan. So the event is Typhoon Morakot in August of 2009. And this wasn't particularly strong typhoon. It was a category 2, but interactions with the topography of Taiwan and a low-level jet coming off of China sort of stalled the system over southern Taiwan for 4 days. And so it just sat there feeding the landscape with rain. And over those 4 days, some of the rain gauges recorded rather incredible magnitudes of precipitation All the red dots that you see on here are over 1.8 meters of rain in those 4 days. Some of them getting over 3 meters of rain in those 4 days. And in the steep tectonically active landscape like Taiwan, you could imagine the impact that had on the landscape, and that was landslides. And in fact, over 20,000 landslides in this area that I'm highlighting over here on the right from a paper from Liu et al. 2011. And if you don't know Taiwan, Taiwan is a pretty small country. You can actually fit it aerially within the state of Indiana. And so to have 20,000 landslides in just a fraction of that island is a pretty massive event. Well, of course, this sediment just didn't sit there. It got washed down into the river systems where we have this cascading hazard. We can see this comparison of 2011 and 2013, where the aggradation just buried this town. And then over in this coastal community, the river almost avulsed over the community, but just aggraded significantly. And so our question in terms of a cascading hazard concept is, what is the impact of this? You know, this is a rather extreme case of a change in conveyance capacity of the channel, right? So you have some sort of cross-sectional area of a channel, and that can hold some volumetric flow rate of water discharge. If you aggrade that channel, if you change the shape of the channel, you change that magnitude of the flow rate that it can contain within the channel before it overbanks and inundates outside the channel. And so we're going to look at this change in conveyance capacity due to this extreme cascade of sediment coming down from the hill slopes. To address the question, how have channel changes following Typhoon Morakot influenced flood inundation and hazard in the years after the event? So long after the event. And we have a paper that we published in Geology last year that suggests the sediment's going to stick around for probably decades in the system. And so it's a long-lasting change in the hydrological regime. So to do this, we're going to use HEC-RAS 2D. For those unfamiliar, this solves two-dimensional shallow water equations, which are a depth integrative of the Navier-Stokes. Uses an implicit finite volume. You can have an irregular mesh that's shaped different ways and in different resolution. It requires inputs of topography and bathymetry, and I'm going to show you how we do that in Taiwan in the next slide. As well as a hydrograph. We're using a very simple hydrograph for now, but in the future, we're going to go to full hydrographs from Taiwan's Water Resource Agency. And then we use a roughness that we calibrate with a known event. So the nice thing about working in Taiwan is they have almost annual stereo aerial photos for the entire island. And so we use structure for motion processing using Agisoft Metashape to get meter scale digital surface models, and the rivers are pretty much devoid of vegetation, so the surface models are the digital terrain models. Also, the dry season when they fly these aerial photos is usually the river is a fraction of the sort of typhoon spanning channel width, and so the bathymetry is a rather minor component in the overall structure of the riverbed. So we use the structure for motion models from aerial photos before and just after, and then a handful of years after Typhoon Morakot, to run this very simple flow hydrograph. Here's the flow rate, and over a 12-hour a couple-day period here, and you can see in the bottom, we have a mesh grid. We upscale our DTM to 5 meter by 5 meter cells. We input at the upstream boundary here on the right, and use this simple hydrograph just to map what the flood inundation extent looked like before and after Typhoon Morakot. And so this is sort of a grid of results. So here is in the upper left here, we have a image of the structure for motion model from 2005 overlaid with what that hydrograph model predicts in terms of inundation event. If we go to 2009, they flew the island about a month after the typhoon. We use that DEM and rerun that exact same hydrograph, and you can see there's a rather a wider extent of flood inundation because of this aggradation and this change in channel conveyance. And that's what we sort of outlined here in the upper right. By 2015, 6 years after, we can see there's some re-entrenching of the flow in the upper reaches of our model, but down in the downstream reaches, this more straight reach, we can see that the channel extent is still inundating far more area than it was prior to the typhoon. And so this is sort of an example, a case example of the sort of cascading effects and impacts on flood inundation. And so our conclusions are these widespread landslide events triggered by rainfall, earthquakes, wildfires can have long-lasting impacts on flood hazards. Channel geometry is not static. It can impact flood inundation for years to decades following these disturbances. I just want to sort of point out that this is sort of a point made by a recent perspective piece by Jim Best, Beyond Just Floodwater, that talking about the future of flooding and understanding and predicting flooding hazards requires us to actually think about the changing channel geometry and all these things that we're going to talk about for the rest of today: landslide stability and sediment transport and routing in these landscapes. And so I will wrap up there.
Professor Brian Yanites, Indiana, thank you so much. Pulling together the sediment in the water there is fantastic. Nice, very nice work. Thanks for the talk. Francis Rengers, Dr. Francis Rengers is a research geologist at the US Geological Survey. I think of him as Mr. Fire, but he is also many other things. Francis, thanks so much for being here.
Well, thanks everybody. These are great talks. So this is going to be a much smaller scale than what we've seen. We're going to go down to like 1 square kilometer basins here. But I'm going to talk about a model to estimate post-fire debris flow timing. And we're going to try and do that with a really simple rainfall runoff model. And as you can see in this photo, wildfires are increasing in the wildland-urban interface. And they produce debris flows and flash floods that cause a lot of damage, like you can see here. So the question for a couple studies I'm going to present are, can we estimate the debris flow peak timing or when that will arrive downstream? So we start with the basics. This is really simple stuff. We start with the conservation of mass. Our input is precipitation. So in everything I'll show you today, we use measured precipitation. For infiltration, again, we keep it really simple. We use a green AMP model, and we're going to have a calibrated parameter, the saturated hydraulic conductivity. That's going to come into play there. For the conservation of momentum, we do both the full shallow water equations, and we try and test the kinematic wave to see if it gets us good enough, because it's a little bit faster and easier to run. So the first study here, we're going to model discharge from hill slope through channels using just Manning's equation. And we have a Manning's N, which is our other calibrated parameter. And that's below a depth threshold, it's static. And then once it gets deeper than our threshold, it starts to decay off. So this is really an optimization problem. We're going to calibrate Manning's N and saturated hydraulic conductivity for a series of watersheds. Here's our study area. This is the San Gabriel Mountains, Southern California. It was burned in the 2009 station fire. We're going to calibrate on a really tiny basin, Arroyo Seco, and we're going to move up to Big Tahunga, which is about 1 square kilometer. And then we're going to test on the Dunsmore Basin. So here's the Arroyo Seco Basin. You can see it's burned. There's lots of rills. There is instrumentation out there to measure rainfall and soil moisture that we use as input for a model. We also use stage measured at the bottom of the watershed, and that's what we use to test our model. So here's what the model looks like. On the top, it's a watershed. The outlet is to the left. Colors are flow depth in meters. On the bottom is rainfall intensity. So this is a distributed model, and you can see we're getting flow depth everywhere in this watershed. So we ran lots of model simulations with variable parameters, and we got these set of best fit parameter values. So here it is on the Arroyo Seco Basin. black line is the measured stage. The blue dashed line is the rainfall intensity. Whoops, there we go. So the first comparison is the kinematic wave equation. And what we're trying to see is when that first peak of our model matches the first peak of the debris flow. And you can see that the peaks match pretty well, although the model ramps up, which makes sense because it's a water only type model. But we're able to kind of get the timing. That's what we're going for here. We missed some of the debris flow surges, but then on the back end, the watery tail, get that timing as well. We also look at the full shallow water equation. We get fairly similar results. So then when we move up to a bigger watershed, Big Tahunga, full shallow water equation here is shown in red. That kind of gets the first jagged peak a little bit better. The kinematic wave is shifted, so it's a minute or two off of the peak, the second peak of the full shallow water equation. So then we apply it to the Dunsmore Basin, and we have two different storms, December 13th, January 18th. Here we're able to simulate that first peak timing. Again, we're not trying to simulate stage here, just matching the timing. We get within about 4 minutes of when you see the debris flow come down. So we wanted to try and refine this model. Here we bump it out and use quite a few more basins. And what we've done is broken out hill slope and channel roughness. And the reason we do that is because for the channel roughness, we can use this VPE equation, and we use a field measured parameter. So we don't need to use any type of calibration for that. We're going to start by still using Manning's N for the hill slope and move to field parameter for that as well. So we run 6 calibrations. The blue line here is our model. And for each of those blue lines, there's actually 6 model runs for 6 different hill slope Manning's Ns. But for most of the watersheds, those just collapse onto a single one. So it's not very sensitive to the Manning's N on the hill slope. And when we look at our test group with our model, we're able to, with our best fit hill slope Manning's N, best fit saturated hydraulic conductivity, match the first peak where we see debris flow activity pretty well. So then we finish out by trying to use only model parameters that are calibrated with field measurements. So here, the black line again is measured stage, and then the orange line is the model discharge, and we use field measurements for saturated hydraulic conductivity, field measurements of a D50 particle to calibrate a Manning's N on the hill slope, and field measurement of the D84 particle size for the roughness in the channel. And on this fully field parameterized model, we can match the peak timing to within about a minute of what was observed. So the lessons learned here are that the kinematic flow routing can produce peak flow timing about as well as the full shallow water equations for our kind of rough warning purposes. This isn't trying to be super exact. The water only model also captures some of the importance of flow timing. And I think what's most useful about this is we can estimate the flow front to within minutes, even during a 20-hour storm. And then finally, we show how to use field measurements to eliminate the need for parameter calibration, which can make this a little bit more flexible. So I'll take any questions. Oh,
great. Thank you so much. No, don't worry. Don't worry. That was fantastic. Francis, there's a very active Google Doc happening right now. And so if you are able to click on the link in the chat, there's a handful of different bullet areas to start asking questions, and Paul Bates gets a gold star because he's answering them in real time. So thanks, Paul. And if others are able to jump in there, please do. You can also raise your hand at the end of this to ask questions directly of the speakers. Thanks. Professor Guiseppe Formetta, can you hear me all right? I think we're ready for you.
Very well.
Thanks so much for being with us. Take it away.
Thank you very much. I hope you can see my screen. And today I want to give a flavor of the model that we developed in the Trento University in the north part of Italy. In particular, we developed these two different hydrological models. The first one is GeoFrame, which is a framework able to simulate large-scale river basin, and in particular, all the components of the hydrological cycle. The second one is the geotop model, and this is the one that I would like to talk about today. Geotop is a three-dimensional integrated hydrological model, is process-based, and is applied at hill slope scale or small basin scale. It receives some input, such as geomorphological information, both horizontal and vertical. In particular, in the horizontal plane, we can define different land cover type and so on. In the vertical plane, we can define the vertical mesh and the three-dimensional grid in which the model solves the water and the energy budget. Here you can see the reference papers of the model. I would like to focus mostly on the three-dimensional hydrological model, core of the geotop model, and in particular, I would like to move first on the water balance. Here we can see that the model is able to solve the three-dimensional Richards equation. It is able to account for a soil anisotropy, about soil hydraulic conductivity, the variability of the layer thickness, and the parameterization of the Van Genuten and the Moalen soil water retention curve can be accounted for. It also has a multi-layer snow cover modeling coupled with the surface energy balance. It accounts for the soil freezing and the permafrost simulation as well, and receives distributed meteorological forcing data. In the basic configuration, we just need the rainfall, air temperature, and eventually radiation. It accounts for the channel routing, and the overall flow is computed by solving the shallow water equation, neglecting the inertia in this case. The soil water balance is coupled with the energy water balance. The model is able to account different fraction of land cover type, the evaporation from bare soil and the evaporation from different vegetation cover. And in particular, now I would like to move to some application, for example, describing some model output. Here is an early warning system on an Italian highway. Here on the left-hand side, you can see the ice and the basin studied by top, and the model is able to simulate the suction head, so the pressure head, at different depth, for example, and in time. And this output of the model can be analyzed in a slope stability, for example, module that can compute eventually a factor of safety. The last application is instead the reproduction of result measure collected in a physical model lab, where we simulate in 3D a system of layered pyroclastic soils. In particular, we have volcanic ash, which are with low permeability, pumices, which are very highly permeable, and finally, again, volcanic ash. So the complexity of the stratification is quite high. And here on the bottom, you can see the measured and simulated pressure head in 3D and in 1D simulation. So the model can be consistently used not only in 3D, but also in 1D. Finally, here I can show you a section of the result obtained, in which we can understand how the infiltration process across the layered soils go on, and the pumices in the in the middle of the hill slope, saturate, building up water table along which the eventual slope may failure. I want to, as concern the cascade hazard, the landslide is one process that can be associated, for example, and for these reasons, I will run to the presentation by Dino Bellugi later on. I also would like to thank you all for the attention. And eventually, if you have any question, please go on.
Thank you so much, Giuseppe, again, in your evening for spending some time with us. And you're very efficient as well. That gives us some time for our very last talk of the session. Lauren Grimley is a PhD student, so thank you so much for being here, Lauren. She's here to tell us about modeling cyclones. She's from the University of North Carolina at Chapel Hill. So thanks, Lauren.
Great. My screen's showing. Great. Yes, my name's Lauren Grimley. I'm a PhD candidate at UNC Chapel Hill, and my background is in hydrology and water resources, but I've started kind of entering this more coastal world, which has a significant number of challenges that's been fun and stressful to address. But I'm going to talk a little bit about that for some of the work I've done for my dissertation. Okay, so I was inspired by this idea of needing to better capture flood hazards. And as it's kind of been mentioned, compound flooding, which is when more than one process happens at the same time, is becoming a big issue, especially when we think of tropical cyclones. But flood risk is currently mapped with models that just assume a single driver, so just rivers or storm surge. But with trying to figure out how to simulate compound flooding, especially at large spatial scales, there really isn't a consensus on what approaches to use or what models. And so for my work, I have selected the superfast inundation of coast model, or SPHINX. This is developed at Deltaris and it's open source. It solves the local inertial equations and includes wind drag. And the reason I was interested in this model is because it had the processes necessary to model these different drivers that are common to tropical cyclones. So there's spatially varying infiltration, precipitation, and wind. There's also a subgrid feature that is becoming more common in surface models that allows us to map the water level and Manning's roughness at a finer scale. So today I'm just going to highlight a study I've done looking at Hurricane Florence in 2018. It made landfall in Wilmington, North Carolina, and caused significant damage from inland to the coast in both South and North Carolina. And on the right, I'm showing my model domain, which is extending pretty far inland, almost to the triangle, which is the Raleigh area. And so this model that I've built is currently a 200-meter grid with a 2-meter subgrid. It is a 23-day simulation and takes about 1.5 hours to run on just 32 cores. But the setup of this model, one of the reasons I was really interested in is there's a automated open source toolbox to generate this from a data catalog. And so it takes in the general information of land use, land cover, soil, and topopathymetry. And the kinds of outputs we're looking at are water level, velocity, discharge, time of inundation, and a few others. For Hurricane Florence, the different inputs that I've used are USGS streamflow discharge at the upstream boundary. And I'm coupling this one way to ADCIRC, which is the advanced circulation model that simulates waves and storm surge. And so this is applied to the downstream boundary of SPHINX. And then gridded precipitation and wind is applied directly to the SPHINX grid. And one of the advantages of this model is I can easily turn on and off these different processes to see how the flood hazard changes. Briefly highlighting some of the results, I've been doing a very deep dive into this validation, and I've been comparing to high water marks USGS and NOAA gauges, and then also trying to get at pluvial flooding. And on the left, I'm showing the model performance in predicting peak water levels compared to high water marks. One area used in South Carolina towards the south is a lot of redder dots. And one of the issues there is I have limited channel bathymetry and also at the estuaries. So that kind of highlights one thing I'll point out is a need for these larger scale models. But then I was also really interested in seeing how well these models, reduced physics are able to predict fluvial flooding, because we're seeing significant losses outside of the floodplain. And so one way I'm trying to do that is using point level estimates of damage to see, are we predicting where flooding caused damage in the past? So I just wanted to show some of the results of this model. So here's the model with just the coastal drivers. So storm surge and wind applied. We see a lot of areas along the coast and estuaries inundated. When we add pluvial and fluvial processes, the extent of flooding drastically increases, and so does exposure. We can also zoom in and look at how these different processes are affecting total water levels. I'm showing two plots, hydrographs of two estuarine communities where black dots are the USGS gauges and then the rest are model runs. The model runs for on the left, there was one community where wind was the primary driver of the total water level that they experienced from Hurricane Florence. And on the right, we see that rainfall was the reason they experienced peak water level and an extended duration of inundation. So this tool is able to show us how those different drivers are impacting different communities across the larger scale. And ultimately, I'm planning to take this and couple it with more on the atmospheric side to see how we can take global climate model output and bring it down and try to get better estimates or an idea of how flood exposure and extents are going to change in the future. And so my main takeaways are, we've got a lot of models, but we need to find ways to validate them for pluvial flooding. We also, that Sphinx is one of them, is Sphinx performs pretty well compared to other large scale inundation models. And it will perform even better if we have channel bathymetry data sets, which is not something that's widely available and makes it challenging to correctly simulate the hydrology. And lastly, Sphinx is great because of an automated setup and it's quick. One of the things that I thought was really important was making scalable solutions, tools that could be applied quickly and easily at other locations. And with that, I am done.
Lauren, great talk. Thank you so much for having us finish so strong. And actually, since you're still here, I might ask the first question of you. I think at the beginning, you really nicely framed the choices and the trade-offs between different models and different levels of physics and so forth. Can you say a little bit more about that? And then I'd also love to have the other speakers jump in terms of, again, what are the key trade-offs in terms of model choice and how that affects the results and computational feasibility?
Yeah, so AdCirc is a very process-based model that solves total water levels due to the coastal processes at a fine resolution, but it doesn't have rainfall or stream flow. So that's kind of, you're picking your battle on when you're trying to decide what is important for the processes of flooding you're interested in. I am curious to test these reduced physics models for smaller events. I think that might challenge them a little bit more than with large scale inundation, and probably amplify the need for better channel bathymetry data.
The other speakers like to chime in on this question? What goes through your head? Paul, I see you're unmuting. Please jump in.
Yeah, I'll jump in. Well, there's been a couple of large-scale evaluations and into comparisons of model types. There's a nice group in Belgium that's done this over a very large number of catchments, a large area. And what we see is what I put in the Google document, that those tests tend to show that 2D models perform best across a variety of inundation situations, particularly in complex, unbounded floodplains. They really show that 1D models and geomorphic or non-model based approaches like hand tend to fall over in those situations and only tend to work well in confined valleys. So I think as we get more evidence, it's clear that for flood inundation, you need to move to 2D modeling. And I think it's pretty clear, like Lauren says, that 2D models need to include the channel bathymetry, because even during a flood, a large amount of the flux is still going along the channel network. So you need the bathymetry incorrectly, and you need that to get the massive momentum exchange to the floodplain sections. In terms of computational cost, I think models like ListFlood and Sphinx, solving similar reduced physics equations with efficient numerical schemes, do reduce the cost of that, but there's no getting away from the fact that these models are expensive to apply at scale.
Since you're there still, Paul, one of the questions to you in the Google Doc was the work you showed was really impressive. Can academics get their hands on it, or others? And you've responded, but can you tell the group?
Yeah, so we make the data available through an academic license. So it has to be for research only, because part of the way we generate the resource to do this work is by licensing the data to commercial people like insurers and NGOs. So giving the data away to academics comes with the proviso you don't kill our business model, because otherwise we're not going to be able to do this work in the future. But yeah, data is available under an academic license from either Fathom, which is the startup, or First Street Foundation, who funded some of the work in the US. The only proviso is that over the US, it's many terabytes of data. So actually handling this stuff is non-trivial.
You've been warned, but also the opportunities out there. Yes, thanks, Paul. Brian, jump in.
Yeah, I was just going to say, I think, the other thing that you have to consider and what level of physics you want your model is the scale of your question, right? Do you want to understand the sort of inundation at the continental or state or whatever level, or are you getting more localized and this farm field versus that farm field, and there's different models that have different sort of bells and whistles that then require more parameterization. And so it's always that sort of trade-off of the scale of your question and which of these different inundation models that one could potentially tap into.
Francis?
Hey, Brian, just to key off of that, I think that's such a great point, because in the post-wildfire debris flow world, we rarely see debris flows happen at scales larger than about 10 square kilometers. And often we're way up in the 1 to 2 square kilometer basins. These are tiny. So thinking about scale is really important for models, because if you have a model that has a 1 square kilometer grid cell, that's your entire basin. So yeah, that's definitely something I think is really important.
Well, Francis, since you're here, there was a couple of questions about the post-fire hydrologic response. One of them is is there a separation between the timing of when runoff begins and the time that a debris flow is initiated? And what are the sort of relevant parameters for capturing that, given that you had such nice results on the timing of those surges?
Yeah, that's such an interesting question. So one of the things we did is we looked at, there's a parameter, this Q star, it's a dimensionless discharge threshold that people have noticed that kind of separates when you get discharges that are above this Q star, you tend to have debris flows. And if it's below the Q star, you tend not to. And one of the cool things about this is we can model this distributed runoff, and then we can go, okay, do we tend to be above our debris flow threshold? And when we look at the stage, we kind of look when it kicks up, we can see like the fraction of pixels that are above that that discharge threshold are usually high. It's like 80% or more. So it seems like we're able to tie runoff to when we might see debris flows through this threshold parameter.
Thank you. And we're just about almost out of time, but I saw Jeff Keck posted a question in the chat. And in the future, please use your raise hands if you want to do it the old fashioned way, pretend like we're at AGU or wherever else, raising your hands, please do that for the rest of these sessions. But Jeff asks, Brian, what about vegetation on the floodplain? Does that matter? Can you put it in there?
Oh, yeah, I was typing out a response, but I'll just answer. In Taiwan, on average, Taiwan gets hit by 4 typhoons a year, and that keeps the channel pretty much free of vegetation. That said, there's been this sort of strange climatological phenomenon the last 3 years, and that there's been a typhoon drought. And so I was just there in March, and there's, pretty significant grass that's been growing in the floodplain. I suspect the next typhoon will just rip that all out anyway. You could put spatially variable roughness to account for those sorts of things into these flood inundation models. And that's my answer.
Cool. Paul,
Yeah.
jump in.
Yeah, Josh, just to say that's absolutely right. You do need to remove buildings and vegetation from the digital surface model. You need bare earth unless you're going to go to very high resolution, at which point you could resolve buildings individually, but you'd still need to remove the veg.
Digital deforestation coming your way. All right, well, I think this is a good chance to just take a pause, and again, encourage everyone going forward, raise your hand, use the Zoom chat, use the Google Doc, has been very active, so really appreciate you engaging. But mostly I just want to thank the speakers. That was really, really fantastic sort of survey of different scales, different questions, and really, really nice illustration of models in a short amount of time. So I really appreciate your time. Thanks so much for being with us here today for the first session of our second day here. Thanks you, speakers. Much appreciated. And with that,